This is Physics 2212, Lab 4, Magnetic Braking. Introduction. The purpose of this lab is to observe Faraday's law in real life, then create a simulated model of our experiment. We will have two parts to this lab, the experimental model and the computational model. The experimental model will involve an aluminum foil roll and a bar magnet. The computational model will be a simulated experiment written in GlowScript. A preview of this lab shows that our experimental model resulted in a time of 2.04 seconds, and our computational model resulted in a time of 1.875 seconds. Introduction. Fundamental physics principles. The first key principle of this lab is Faraday's law. Faraday's law states that a magnetic flux that changes in time creates a non-Coulomb electric field that generates a voltage. This can be seen down here in this equation. It says that m equals the negative change in magnetic flux over change in time, which is equal to the negative derivative of the integral of b dot n dA. Another principle in this lab is the Biot-Savart law, which states that a steady electric current creates a magnetic field. We will see this in the rings that are around the aluminum foil that generate a current that come from the bar magnet. The last physics principle involved in this lab is Newton's second law, which states that force is the rate of change in momentum. The experimental part of the lab, we will use a roll of aluminum foil and a bar magnet to see Faraday's law in action. To simplify the explanation, we break the aluminum foil into many infinitesimal rings that add up to the total length of the tube. As the bar magnet approaches the ring, the magnetic field from the bar magnet causes an increase in magnetic flux for the ring, which results in an induced current in the ring that provides a magnetic force in the opposite direction of the magnet's motion. This results in a slower descent seen in our experiment. Right here on the right is the ring of the aluminum foil that we take and we find the induced current of. We see that the bar magnet is moving closer to it, resulting in a larger magnetic field. This results in the induced current seen in the ring, which then results in a magnetic force pointing the opposite direction of gravity. Experimental model results. For this part of the lab, the system is the bar magnet, the surroundings are the aluminum foil and earth. For trial 1, we had 2.17 seconds, trial 2, 1.89 seconds, trial 3, 2.04 seconds, trial 4, 2.08 seconds, trial 5, 2.02 seconds. This averaged out to a time of 2.04 seconds. Computational. Below are some of the parts of the code. This first part here shows us defining the bar magnet, its mass, and its dipole moment. Our magnetic dipole moment is taken from lab 3, the value we calculated to be 1.217. This part here shows us finding the magnetic force taken from each ring as we iterate through each ring of the aluminum foil. This last part seen here shows two functions that are defined in this code. The first one, finding the magnetic force from the dipole magnet. The second part, finding the change in flux and over the change in time. Computational model results. When we run our code, we are given this output. We're given a velocity versus time graph, which shows a steady velocity in the time that the bar magnet is in the tube. The time that it takes for the bar magnet to enter and then leave the tube is calculated to be 1.875 seconds. This image on the right shows what the tube looks like as the bar magnet travels through, with a magnetic force and the induced current being shown in blue and red, respectively. Possible sources of error and discrepancies. Possible errors in the experimental part of the lab include human error when measuring the time of the drop and inconsistencies in the drop height for the magnet. Possible errors in the computational model could be the code doesn't account for air resistance, which could be a large contributor as a force that slows the magnet. These factors together could be the reason as to why the computational model and the experimental model did not exactly match, as the computational model was 1.875 seconds, while the experimental model was 2.04. Two final questions in this part of the lab. The first one asks, what if the resistivity of the conductor was reduced as close as possible to zero? What would change? If the resistivity of a material decreases, the conducting properties of that material become better. So, if the resistivity of our aluminum approached zero, the induced current in our aluminum foil would be greater, creating a larger magnetic force on our bar magnet, slowing it down further. Our second question asks, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, our rings would no longer be complete loops, meaning that the overall current in our aluminum foil would be lower. This would create a weaker magnetic force, meaning the magnet would fall faster.